I just wanted to say on behalf of Brown Physics, the Center for the Fundamental Physics of the Universe, and behalf of myself and panelists, welcome to this winter school. The target participants for this school are graduate and advanced undergraduate students in physics. Really welcome. We are really trying to ensure that in this period of a phenomenal sort of intellectual growth in terms of our understanding of what machine learning and artificial intelligence is capable of, that it's very important for those of you who are just beginning your journey within academia and in particular in physics, that we are making it sort of maximally accessible to you. And to that end, over the next 3.5 days, we are going to present a number of modules to you, which will demonstrate hands-on examples of using machine learning techniques in physics experiments. So I just on the basic administration, I'm pretty sure if you're here, you've already understood this, but it was just simply to point out that the central page for this entire meeting is run through an Indico server. It's hosted here at physics.brown. Just simply the AI Winter School 2025. You can get, if you forget that address, you can get it through the Google, simply searching for it. But in order to fully participate, you do need to register. So please make sure you use the registration system under that site. You will be granted the sort of Google Drive access, and that will allow you to be able to see all the material. There are some instructions that it's important for you to follow, because that will make your participation in the workshop as smooth as possible. There's a README file that describes all of that. I do want to mention, obviously, the support from both Brown University, with which we're based here. It's an Ivy League university here in Providence, Rhode Island. For those of you who are not familiar with Providence, Rhode Island, it's somewhere you will drive past as you simply travel from Boston to New York. We're nearly halfway between the two. The Department of Physics, the chair, Vesna Mitrovic, the department itself has 31 faculty, over 100 physics research graduate students, as well as many, many undergraduates. And I do want to thank so many of my colleagues who have contributed to this school. And then lastly, and this, I really have to make a sort of big deal about this, but thank you so much to the CFPU members, in particular our center administrator, Errol Green, who has done an enormous amount to make this winter school possible, and continues to help you in many ways as we can, for all of those of you who are participating. The numbers of you who have responded this year is simply enormous. We have over 1,000 people who are sort of directly involved, registered. And also you'll be hearing from Sean Dubé, who will be making the first presentation. It was also thank you to him for all the work he's done to make this school possible. So I really want to now go straight to our panel. The topic that we thought would be appropriate, given the many of the registrants that we're hoping, or participants that we're hoping, is really trying to develop or discuss this business of what do we need AI to be capable of to really propel physics forward. We're trying to deal with this right at the moment, but we will also, I think, indulge ourselves and speculate a little bit about where AI may go. And of course, as I think so many of you are discovering, the rate of evolution of the AI, the sort of exponentiation, is so dramatic that a question like this changes rapidly year to year. The three members of the panel who very kindly agreed to participate are shown. This slide deck is directly available in your in the school's main working drive that all of you should have access to alongside the modules. It's also, this information is directly available on your sorry, on the Indigo, on the main conference page. But as I say, Kyle Cranmer from University of Wisconsin-Madison, as you see, professor of physics. All of our colleagues on this one are professors of physics, working in Kyle's case in particle physics and also as a director of Data Science Institute at Wisconsin-Madison. We then have Jim Halverson from Northeastern, who again, comes through the sort of particle physics and machine, but has expanded into the machine learning route, and as you'll see mentioned, in a number of places that the recently established AI Institute for Artificial Intelligence and Fundamental Interactions, has been established in New England, and is one he's directly involved in. And then lastly, Max Tegmark from MIT. Max has, I think, been well ahead of the crowd with respect to the importance of understanding AI and machine learning, and has not only conducting a sort of significant research program, building, having moved or having worked for so long, which is where I first got to know him in cosmology, and then now doing so much in machine learning. And if you haven't read Life 3.0, I do recommend his writing. It's extremely interesting. So without taking any more time, I'm just going to sort of kick off and start asking the sort of appropriate questions, really to get our panelist moving. Sorry, I've just got to bring it up on a different screen here. So I thought, initially, and please, panelists, step in as soon as or you'd like to, although maybe we should start, if we want, in alphabetical order initially, but then we'll move to a far free form. But I thought it'd be interesting to sort of consider directly to the question that the panel has title, which is what AI developments right now are most needed to enhance the type of analyses and reasoning that are common in physics, and how best or what areas of AI are already most helping us. So possibly at this point I should surrender the screen, and Kyle, maybe if you want, you'd like to start off.
Sure. Yeah, no, happy to. I think, it's interesting, and well, I think in particle physics, also in cosmology, many areas of fundamental physics, people have been using machine learning of one style or another for decades. So in that sense, it's not so new, but most of the applications that were used were some type of predictive task, like you were either trying to estimate the property of, like a galaxy or, what have you, or you were trying to do a classification type problem, like tell the difference between signal and background and your experimental data. And there was really very little use of machine learning, I would say, in anything kind of theoretical physics, because most of the problems you had didn't lend themselves to that kind of predictive task. And that's been what was happening for decades, and that will continue, and it's getting better with things like deep learning. But I wouldn't say it's the kind of like qualitative type of change that I think is what's drawing a lot of the interest. When I think the kinds of capabilities that are coming up now that are pretty interesting, one is if you think about like how, say, we're searching through the data at the Large Hadron Collider. Previously, you were always driven by hypotheses where you say, like, I'm looking for the Higgs boson or supersymmetry, and you had a template for what you were looking for, and machine learning was assisting you to do that in an effective way. Now there's some interesting stuff about looking through the data to try to find anomalies, and that's of a slightly different character, but still relatively traditional, I would say. And then there are things that we're kind of hoping for where we really get somehow some very new capabilities. And I think as a general I think there's a lot of potential for that. But one thing that I would kind of carve out, which is interesting, is that if you do find something interesting in the data, uh, what do you do next, right? Are you going to build another experiment? Or are you going to do another survey? Or what's going to happen there? And right now, it's really until we get to the point where AI type might be able to automate that as well as currently, it's really humans' job to look at whatever that anomaly or deviation from the data or whatever unexpected tension that you might find, and then think about, okay, well, what's the follow-up experiment that I want to do? And the way that we connect that is not really through computation. Usually it's really usually much more through reasoning, like you kind of inspecting what kinds of phenomena might explain this and what kinds of experiments might I do or what kind of observations would help me tell the difference between multiple hypotheses. So I think when we start thinking about hypothesis generation, like what could explain this, what's different, and experimental design, those are things that basically we've never really had AI involved in that. That's basically almost always been a human task. And so I think for that reason, interpretability is pretty important. That's like, if you want to put a finger on why do you care about interpretability, there's many areas, like if the AI is getting you like in a self-driving car to get you to the airport, maybe you don't really care how it's working so much inside. But if you're a scientist and you don't have AI that's powerful enough to come up with new hypotheses and design new experiments, then it's very important for humans to be able to do that. And I think in the longer term future, maybe the AI has its own way of expressing theories, or maybe it uses our language for expressing theories. That's an open question, I would say. But at some point, the AI might start to actually generate hypotheses and reason about what kinds of experiments would be good for testing those hypotheses. But and I think in the transition that we're making now, it's going from really just like purely predictive type tasks to something more powerful. But that's kind of, I'd say, the intermediate step.
Yes, absolutely. Jim.
Yeah, I agree with a number of the things that Kyle said. One of the things about this sort of question, I think it was advertised to me with an italics on the really. So I was thinking about this at a meeting last week. What does it really take to really have physics move forward? And it kind of caused me to pause a little bit, because at least, the Nobel Prize in Chemistry this year would have you believe that it already has really propelled chemistry forward. And so it sort of started getting me thinking about some of the differences between physics and chemistry. Speaking as a string theorist and a sort of a formal theoretical high energy physicist, one of the things that I think is different about our community than that community is that we don't have a super sharp, well-defined question that everyone agrees is super important computationally, the way that the protein folding community did. But I think I mentioned this because I think it's sort of already clear that ML and AI are in a place where you can really have substantial scientific results. And so in my community in string theory, that's sort of a question for humans to think about. But I think the other side of this coin that Kyle was already getting at is that robustness and interpretability are absolutely essential. So interpretability is definitely one side of the coin. Definitely, if you imagine you're in a situation where you don't necessarily care about interpreting, though, which is something that as a physicist is hard to give up, you might still ask about robustness of the results. Can you really trust a result coming from machine learning in a way that would satisfy a mathematician? So one of the things that's been happening in recent years, going back some time, but it's really accelerating, is the interests of so-called pure mathematicians, whatever, however you classify that, in these sorts of techniques. And one of the things they're generally concerned about is how do you get really robust results? So they're in the sense of provable results that either could be put through a system that is actually proving theorems itself, or alternatively to bring a human into the loop based on some ML-inspired idea. Kyle brought up this idea of hypothesis generation, which is a really interesting idea. That's something that has been one modality that's been happening for a little while, but something that maybe he's getting at is that with the current round of LLMs, you might have a little bit more of the machine doing the hypothesis generation, as opposed to the old thing, which people were doing, which is to have some ML algorithm that, you open the box and you have a human analyze what it learned and have the human come up with the hypothesis. But to just put a cap on it, I mean, I think robustness and interpretability are two of the key things moving forward. And I think there's a lot of room for improvement. So,
Max.
Yeah, I agree with everything that both Kyle and Jim said here. And for those of you listening to this, I think you should be both very excited about the possibilities of AI to help you, and also a little bit terrified about where this might go, because of course, what you really, really want is to have machine learning give you wonderful tools that help you become a more productive physicist. But you would kind of don't want the tools to get so good that they can just replace you entirely on the job market. And they maybe even become something that humanity loses control over, and as was mentioned in the beginning by Rick Gaitskell, even though stuff like this, 10 years ago sounded like totally sci-fi, we have to remember that 10 years ago, actually even 6 years ago, something as good as ChatGPT 03 sounded like science fiction too. And so it's happening fast, and I want you all to listen to this, to take that as encouragement to be really nimble and adapt so that you quickly, so you can use these things to your advantage. I think it's also, even though we're talking now about what can AI do for you, to also ask yourself, what can you do for AI? The founding vision of the center that I have the honor of being part of together with Jim, that we have here at the Institute for AI and Fundamental Interactions, is that AI for physics is really useful, and that's what we're talking about here, but physics for AI is also really useful. So when you do physics, you actually have a unique set of skills which can really help the AI community. We heard from both Kyle and Jim, the value, for example, of more interpretability of AI systems, having them be better understood. Physicists, I would argue, have a much higher bar on what we mean by a system being understood than engineers do. And there's already been a lot of really good papers by various physicists that the AI community appreciates, where physicists study machine learning systems and figure out ways of understanding them better and making them more transparent and so on. And then to connect back to this core of the question here, what can AI do for you, and how is that going to improve in the very near future? Just to add a little bit to what Kyle and Jim said, historically, we started out in the 50s and 60s and 70s and 80s with a lot of logic-based AI, more close to formal methods, improving things and so on. And then the big recent revolution has been instead in machine learning with neural networks that kind of intuitively can guess stuff, but they're often wrong. And I think what we're going into now is a very exciting merger of these two approaches, where you can use machine learning to find patterns in your data, maybe to help generate hypotheses, and even try output programs or proofs that may or may not work. And then you marry that with these older techniques, including formal verification, that can actually check if it makes sense. I think all of you listening to this probably recognize this interplay between these two approaches happening in your brain all the time. Like, you have some idea, and then there's like another part of your system, maybe what Daniel Kahneman would call system 2, that swings into action, is like, nah, that makes no sense because of this. But wait a minute, that's interesting, but well, what about this? And then you check things, and maybe you write it down on paper, and you make it more rigorous. I think we're going into a phase where within machine learning systems, we'll be able to have this interplay. We're even seeing, for example, ChatGPT 03 doing a bit of this, where it's not just giving you, the user, back out what first came out of the intuitive part of this, the transformer, but rather there's a whole chain of thought where it reasons about it and critiques it maybe a little bit, and then goes into where we want to be. And I think this is really promising for physics, because ultimately, as scientists, right, we come up with hypotheses for there being patterns in our universe, and conjectures for how these patterns might be describable with physics equations and computable in various ways. But we don't stop there. We go back and check our stuff. First, we check for internal consistency of the theories, try to prove stuff, and then we go check against what nature has to say about it. whether our predictions are valid or not. So in short, I think we're heading for a very exciting merger, which is kind of at peak velocity right now in 2025 of the system one style neural network based AI with formal methods. Pure mathematicians, you asked how to define them. Terence Tao is probably the first one that comes to my mind, and he's gotten very excited about proving stuff about math, and there's absolutely no reason you can't prove stuff about code. I would predict that just as AI has revolutionized our ability to prove things about, or to produce text and to produce images, and beginning to revolutionize our ability to produce code, it's totally going to revolutionize our ability to also prove stuff about math and physics. And we should be the first to exploit that.
A theme that you all, have raised very clearly. Obviously, the generation of understanding that comes through or conjectured from AI systems. I mean, is there a danger that we, the humans, become overwhelmed by the simple volume of hypothesis and apparent structure that is being generated through AI, but unfortunately, may have some flaws in it that wouldn't pass this robustness criterion, but simply because of the volume of that material, it becomes almost impossible to resist. And in fact, researchers become victim of not wanting to be left behind, should we say? Because I think yes, you've all highlighted this idea of how critical in physics robustness and interpretability is, and yet, one does have some, should we say, possible concerns that may get swept away. As any one of you, please, if you'd like to, please, Max. Yeah.
I was just going to say, one of our best friends as physicists is Occam's razor, and I think we can put Occam's razor on a very firm, rigorous footing through the lens of information theory, where for every physics model you have that's supposed to predict something, you keep track of not only how inaccurate it is, where more inaccurate is worse, but also how complex it is. It's measured in bits of information to describe the method, where more is worse. And then you get sort of a Pareto frontier, complexity versus inaccuracy. And what we physicists tend to love are things that are both remarkably accurate and remarkably simple. And traditionally, Occam wasn't talking about this in math terms, but information theory is something machine learning can totally help us do, and help more automatically prune out super complicated things, and have us humans only look at the ones that we're going to find simple yet predictive. So we can basically triage what we need to look at.
Yeah, I mean, I think I agree with that. I mean, even without the underlying complexity and Occam's razor aspect of it, I mean, the first part, I mean, it's absolutely, you can be overwhelmed. I mean, I think that's true even before AI, just any kind of automated setting, or you think about even going back, I mean, to something like, decades ago when we were entering the Large Hadron Collider, we had theories with supersymmetry with, quite a few adjustable parameters. They seem very tame by today's models that we might dream about, but you're dealing with 20 or 100 free parameters, and the phenomena that can describe is very complicated. And then you start thinking about how the experimental community went after it. I mean, it feels very kind of pedestrian. I mean, there's a very small number of kind of benchmark models that were being studied. And if you want to, you can certainly, with just computation and automation, you can start to attack many more. But as you do it, you definitely need some infrastructure, or you're going to quickly be very overwhelmed. So I think it's also kind of important to keep in mind that many of the transformations that we would like to see, or hope might happen because of some AI thing, well, for them to really happen, they're going to need to come along with some pretty major, both infrastructure changes and potentially some, maybe it's not that all the graduate students are replaced by AI, but even if you still have human physicists involved, there's going to maybe need to be some sociological restructuring. And, a lot of the big collaborations are pretty slow about that. On one side, you can be very kind of critical of like how kind of slow and silly the kind of human approach is, but at the same time, somehow there's something important there, which the AI researchers can learn from, is like, how have we made so much progress understanding the universe with effectively zero compute and like very limited amount of data? I mean, as humans, like, compared to the kind of stuff that we're talking about with modern AI systems. And it has a lot to do with some kind of like being able to move between different levels of abstraction and reasoning, and these kinds of Occam's razor stories and consistency, and a lot of things that you're starting to see the beginning sparkles of and modern AI systems, but compared to what have allowed, what's allowed humans to understand so much about the universe through kind of the tradition of physics is largely missing. And I think that that is not just about understanding the world. It's about like, lots of things that AI would aspire to do in terms of being very data efficient and reasoning in different contexts and all sorts of things like that are, and so I think, also in terms of what can you do for AI, I think somehow physicists taking a very careful look at what we do, like introspection on a personal basis and as a field, to think about how has it we've been so successful with like relatively sparse data and relatively small computation historically, and how do we incorporate some of those themes into AI systems? And I think, Occam's razor is certainly a piece of that, but there's other parts to that as well.
Yes, Jim.
Something I would sort of add into the discussion is sort of the question of breadth. So what I mean by that is, yes, we absolutely need to be careful to not let ourselves be misled by things that large language models are saying, especially when you ask it a question and 90% of the answer might sound reasonable and you really have to read through the 3 paragraphs of text to see if there's an issue. But one of the things that has been out there for a while is different sorts of techniques where you can really fine tune a little bit more. You can have an ML technique that is really addressing one particular type of problem. And in cases I know of, that's where robustness is actually a lot easier to obtain, to trust, etc. Large language models are so good at knowing so many things. In some sense, it's, some people say like the smartest undergraduate in the world or something like that. But that's really about the breadth, about how impressive it is. So one of the things that I think the community would be wise to distinguish is that, we know it as people working in this area, but artificial intelligence did not start in November of 2022 when ChatGPT came into the world. And there was already a host of techniques that were already very robust and fine-tuned. Out in the public eye is these sorts of techniques that win at Go and chess and the like. And those are robust and rigorous in an appropriate sense. They're just very fine-tuned to a particular scientific problem. And so as I think as a scientist about these questions of robustness, I try to think about the breadth of the techniques that are being applied. The broader it is, the more there might be to obtain in terms of reasoning skills. But things that are really fine-tuned by domain experts and interpreted by domain experts, I think there's a lot more possibility in terms of ensuring robustness. So I worry about these concerns of getting overwhelmed by garbage, so to say. But I think if we're careful about it and we know what we're doing, we can have success. So,
thank you. Thank you. And I want to say at this point, I appreciate people typing into the Q&A box. We will get to those questions. I'd just like to, or some of those questions, would like to put our panelists, give them an opportunity to talk about maybe a specific area right now that they are either involved in or they're aware of that they think is exciting. Is exciting the panelist concerning direct application of machine learning, possibly either because of its that it is proving surprisingly successful, or simply maybe that it surprised you. But I think, we are talking anecdotal here. You don't need to provide a completely sufficient explanation. But I think, again, given the audience we have, it would be fantastic. If you do have something you want to mention, that you're aware of that's going on that has particularly surprised you as an academic, interested you, which as I always say to students, is the key to being a good academic, is finding things that are genuinely interesting to to talk about and explore. But anyway, please, Max. Yes.
Yeah. Be delighted. I'll mention two things briefly. The first is the field known as mechanistic interpretability among AI nerds, which basically means you take some AI system that's doing something interesting and smart and try to figure out how it actually works. I think of mechanistic interpretability either as just artificial neuroscience, or more appropriate for us today here is just, physics itself is really just mechanistic interpretability applied to the universe. We look at something interesting happening and try to figure out what are the equations, how does it work? And this field has just totally exploded in the last 2 years, I would say, from being pretty fringe to now being widely recognized as it being actually a field. So much progress. We had at the latest workshop I was involved in organizing at a big AI conference, we had like 200 poster submissions, and it's really, really growing. And this is an area where physicists can contribute greatly. The field has now successfully gone from us saying we have no clue how transformers work to, for example, the existing maps of the geometry of how all the concepts, many of the concepts that they've learned are stored in a high-dimensional space, all sorts of mechanistic interpretations of how they actually work, so I would just advertise that it's a very easy field for someone who likes physics to get into a bit. The second thing I wanted to say is automatic theorem proving with machine learning. This is something my group at MIT is also focusing very hard on right now. Traditionally, the focus has been on using AI to prove stuff about math. There are benchmarks with the order of 100,000 theorems where the automated systems were able to prove maybe 1% of them. And now it's over 70%. So great progress. Whereas for proving stuff about physics, not so much. So this is a fantastic opportunity for people to get in early and start thinking, what would we even mean by proving stuff about physics? And how can we use this? How can we define the machine learning task? Can we make benchmarks with large sets of physics problems that we want AI to try to tackle, and I'm quite confident that if we can do this, we'll very quickly, we'll see a great improvement in how fast we get these kind of tools. And as Jim said, this would very clearly involve marrying together modern machine learning techniques with the more traditional ones, which are more based on formal methods and rigor.
Jim, you want to go? Or?
Jim, Kyle,
Sure. Yeah, I'll go real quick. I mean, there's so many interesting directions. The question was about scientific directions where there's been real progress. So in my community, one result that I'm not really involved in, save one paper, is something called Calabi-Yau manifolds. So this is the type of manifold that, if you're not a string theorist, that you might have heard of in string theory. They're the types of manifolds that, if string theory is true, might describe the curled up extra dimensions. And what's been remarkable, one thing I think, is that for 40 years, string theorists have been talking about Calabi-Yau manifolds. And in the case of interest, which is the one where the manifold's compact and you can make it very small and curl it up and so forth, we don't know, in the cases of interest, of a single analytic metric. And part of the breakthrough the last couple of years is that people are using neural networks now to give state-of-the-art approximations of these so-called Calabi-Yau metrics. There's a theorem that guarantees the existence of these metrics. Yau won the Fields Medal in part for that work. But we really don't have an analytic formula. And so the fact that neural networks are able to model this thing for the first time is, I hope, going to lead to really significant results, both in the math of Calabi-Yau manifolds, which is called algebraic geometry, pure math type of result, but also in the physics implications of string theory. And I can't emphasize enough, the metric is the fundamental object on a Riemannian manifold. And to go 40 years, without really being able to do much with it, and all of a sudden to be able to make progress is really, in my opinion, a remarkable breakthrough. Another thing that is definitely a major interest of mine is sort of ways in which machine learning theory interacts with theoretical physics. So we talk about AI for physics as the normal direction, and then sometimes we talk about physics for AI. And what I have been very surprised by, to use the word that you looked for, Rick, is ways in which machine learning theory itself sort of sheds light on physics. So there's something going back 30 years in the machine learning theory literature called the neural network Gaussian process correspondence, which is basically just a way to, maybe I won't get into the ML aspects, but in physics language, it's a way in which neural networks are deeply related to free field theories. And then from there, you can sort of start to ask about how, if that's a free field theory and some appropriate large n limit, how might you start to turn on interactions in these setups? And are some of the things in machine learning theory leading to new perspectives, either on quantum field theory, which is a major interest of mine, or alternatively on some of these mathematical results that are emerging? So I think something where there's a lot of room for more work is sort of machine learning theory and how it interfaces with math and physics.
Thank you. Kyle.
Cool. All right. So I have a few. I'll try to control myself. But so one of them I'll say is this kind of broad area I call simulation-based inference, which is a pretty generic setup, but where in many areas of science, so certainly in like particle physics and cosmology, you have a very good forward model of how you think, like, you know, the universe evolved with time, or how in particle physics from like the initial hard scattering, how particles will propagate into, you know, through the detector into electronic signals that you're actually collecting. And in the end, you know, just like Max said, there's this kind of the mechanistic interpretability problem is basically a big inverse problem. Given what you're observing, you want to infer something about the mechanism, and you don't get to see all those details. So it's unlike a neural network where you can probe what's going on inside. In physics, we have a lot of stuff you don't get to see inside. So these are sometimes called like latent variables. And so those are generally very, very hard inverse problems. And this is where that connection with statistics is very clean. Like there are statistical problems that you want to do, like measure, you know, some property of like the Higgs boson, or something about, you know, the fundamental, you know, parameters of lambda CDM cosmology or something like that, where that inverse problem is actually very hard. But we can run simulations in this sort of forward direction. And so machine learning is giving us this capability to be able to solve those inverse problems and to be able to work kind of more natively with the raw data, instead of having to sort of invent sort of good observables that might throw away a lot of information in the data. And there's a tension between capturing as much information as in the data and being interpretable. And so like exactly what that playoff looks like is an interesting thing. But those technologies, you know, I had some kind of early works on those just about 10 years ago now already. The first paper in Atlas and CMS came out this year. So it took a long time to kind of hit. And cosmology and astrophysics, those techniques are just like going crazy. I mean, there's tons and tons of papers, but you also see that same framing being applied to computational neuroscience, epidemiology. So it's like a really nice abstraction that is like useful in a whole host of different fields. And I think it's a sign of one of the things that, you know, AI is empowering, but it's in a relatively traditional setup, I'd say. Another one that's kind of interesting, but I'll just call it out, is that I got involved in this on the theoretical side for people like that do lattice field theory. So this is you sort of know what the theory is, you know, you have your Hamiltonian and et cetera, and you're in this non-perturbative regime. So you can't use like Feynman diagrams and perturbation theory. So it's a computational problem. And that's actually, physicists invented a type of, well, kind of the original Monte Carlo, and then later what's called like Hamiltonian Monte Carlo was invented for this problem, because it's like basically, I think arguably the hardest sampling problem that anyone's ever worked on in the sciences. And so recently we started using generative AI tools to try to come up with like the next generation of very good sampling procedures. So that stuff is really cool. And what's interesting about that is that those techniques are being used in things like lattice field theory, like lattice QCD, but they're also being used in areas of like molecular dynamics, where you want to understand, you know, some molecule that might have like a metastable state, or like a drug, and you want to know like how stable is this thing. And so you get a set of techniques again that are like useful in a number of different areas. So I think that's pretty cool. And then the last thing that I've been involved with recently is a little bit more like what Jim was talking about, which are these very theoretical problems. So some stuff with Lance-Dixon and sort of whatever N=4 super Yang-Mills theory, where we're trying to calculate scattering amplitudes at very high loop orders in perturbation theory. And we're using AI techniques to try to basically guess what the answer is. And there you do have something kind of like a verification. It's not really like a theorem prover, but you still have a way to get a certificate of correctness. So this is the first stuff that I've done personally where the AI is not, it's not trying to like model something numerical or like a continuous function. It's really like trying to guess something discrete, and then you have a verification. So it looks more like math. And I think that's interesting. And one aspect of it that's interesting is that in this example, most machine learning is cast in a statistical language. Like there's a distribution that the data is being drawn from. And many of these examples, like the one we're working on, we have one example. We only have one example. And it's like when you see a sequence like the beginning of the Fibonacci sequence and you're supposed to guess like how does the sequence continue. It's kind of an underspecified problem, right? There's lots of ways you can continue that sequence. But again, this sort of Occam's razors ideas and et cetera, and seeing that AI and machine learning might help us both continue the sequence, but also find like what's the underlying recursion rule that tells us something deep about the theory is super cool. And then, sorry, at the risk of saying too much, the last thing I'll say is that for a long time I was interested in following what was going on in language, but I was not really I didn't really see it affecting my work so directly right away as a physicist, at least. And there's this adage that maybe that like causation and correlation are not the same thing, right? And so there's an important fact that kind of everyone here should know, which is that even if you have an infinite amount of data, there are only a certain kinds of questions that you can answer. So even if you have a perfect model, infinite compute, infinite amount of data, you can answer questions that are essentially correlation type questions. But if you want to ask a question that's really about causation, you need the ability to do an intervention. And you can't just get that from the data itself. You actually need to interact with the world, and that's what physicists do, right? So that the role of causality is super important. And but what's interesting is that language is, in some sense, when you train ChatGPT on all this language on the internet, it's just data, right? However, that data is special kind of data. Language is full of things that have semantics that tell you about interventions that were done. If you ask ChatGPT, like there's broken glass on the ground and milk, what do you think happened? Right? It will probably guess that someone knocked the glass of milk on the floor, right? So somehow all of the language that tells you about different kinds of interventions and how things relate to each other unlocks this kind of more powerful type of reasoning, but it is also in the data. It's just explicitly, like the interventions are explicit. And so you can learn about causal systems if the interventions are made explicit. And I think that's one of the things that's like super powerful about language. And I think what we're starting to see that might allow language to do things like hypothesis generation, experimental design, control multiple different kinds of systems and multiple modalities of physics data. I think that's really profound, and somehow my appreciation of language is like really grown. Even though it was pretty high out to begin with, it's even higher now.
Absolutely. Now, I wanted to pick up on an area that has come out in the Q&A, which is obviously, and I've seen students do this, hoping to use sort of anomaly detection, when they're presented with large data sets. So this is very much a sort of practical question. Obviously, there seems to be a fair amount of desire to be able to throw large data sets at networks and then have them bring out anomalies in that data. I was wondering if you, I'm sorry, I went pre-biased by giving my own opinion on this, but what sort of experiences or how confident are you in that?
I got to say something. So one is like anyone who's interested in anomaly detection before using machine learning techniques really needs to do themselves a favor and spend a little bit of time reading up on goodness of fit testing and classical statistics, because it really is the same problem. Like you have a null hypothesis, but you don't have an alternate. You're trying to find anomalies or that are kind of differences from the null hypothesis without specifying an alternate. And there's just a kind of very simple kind of impossibility type statement there that you can't have any kind of anomaly detection that's kind of universally good for all alternate hypotheses. And so So in some sense, what people want is something that is kind of clearly not achievable. So something that's kind of like good for, that's going to find anything and be powerful. And so I think any effort in anomaly detection needs to first be grounded in that kind of basic impossibility result. However, at the same time, you see all sorts of amazing stuff. And so that's partially because once you start to say, like, I'm not interested in alternate hypotheses that you might call like unphysical, because there's like fluctuations that have no rhyme or reason to them. They're like electronic noise or something like that, or like features that are like more resolved than your detector resolution or something that's not physical. You can start to, in statistical terms, you say start to regularize the class of hypotheses that you consider your alternates, and in some kind of Bayesian way, you're starting to put sort of a prior. But previously, we would do the full extreme, like this. I'm looking for the Higgs boson exactly of the standard model, and that's like the super extreme. There are places in the middle where you sort of say roughly what it is that you're looking for. What kind of features are you hoping might exist in your alternate without being super specific about it? And there somehow the machine learning techniques are doing that, but implicitly. And you don't have very much control over how they're regularizing the class of alternates that they're looking for. And so you don't have necessarily good control over them. So what we as physicists need to do is figure out like what's a happy medium where we can say like, I'm looking for deviations from the null in the data, but they should have these kinds of rough features without being super specific, like here's the Hamiltonian or Lagrangian for my particular process that I'm looking for. And that I think is super, I'm very excited about that, but most of the work is not there. It's more like, let's come up with a new neural network technique and stick it in there and kind of hope that we're going to get this unachievable, panacea.
I completely agree with Kyle there. And in a sense, we humans, our brains, you mentioned before that we've been doing a lot of stuff with very small data, but actually, the number of floating point operations that each of your brains does in a lifetime is about 10 to the power 25, which is a huge number. Only ChatGPT-4, that was the first large language model that in its training got up to 10 to the 25. Now we're at about 10 to the 27, I think, with the new Gemini 2. But one of the things that our massive computations have gotten good at doing is useful anomaly detection, right? We don't pay much if we're walking around in the dark and the light conditions change a little bit. Like there's a lot of changes to the bits that came into our retina, but we don't care about that. Whereas if we see something where there's a pattern, where there is some structure in the thing, like maybe there's a ball flying towards us or some weird guy running after us or something, that's when we get very interested. And I think I agree with Kyle that rather than looking for a panacea that doesn't exist, if we or you were listening to this can put some more fundamental thought into quantifying information theoretically, what it is that what kind of anomalies we're actually looking for. This is an area where I think there's a lot of low-hanging fruit, but a lot of machine learning people haven't really worked much on it at all.
Yes. Jim, do you want to add anything there?
Maybe not extensively, but one thing that is coming up in mathematical context sometimes where, we mean something different by an anomaly in a data is some very special feature of some system. One of the things that's limiting certain areas in topology right now is that there are algorithms for generating data, but there aren't algorithms for generating data conditional on certain properties being satisfied. And so I'm using the notion of anomaly very differently there because it's an anomaly in a sort of a theoretical data set, and we're sort of searching for a needle in a haystack. Yeah, I'm not thinking about it in an experimental context, but it is true that those sorts of generative models in mathematical data sets are really only starting to be explored. And there's definitely one project that if only I could do X, Y, and Z, where that's a very specific thing, conditional on this anomalous thing, I would be working on that full time right now.
So in terms of Q&A, there are a number of questions people posed about LLMs. What I would advise is do attend especially the session. We have 2 sessions, both of which are going to look at augmentation of more traditional LLMs on specific physics, material, and the way in which that goes at a very practical level. So I think for those people who are asking questions about that, I think I would possibly suggest that's going to be the great way of you getting some of those questions that you're asking about LLMs. somebody has, a couple of people actually have asked about implications for job market. Very practical. I know, you know, that obviously is an area we could talk probably for an hour just in itself, but I'm sure it is something that is on the minds of you know, many of the physicists who are training. Is there, you know, if we look, and this is also an opportunity to maybe look sort of, you know, 5 or 10 years hence, and I, you know, realize that's a cursed place to ever have to try and occupy. But would any of you like to sort of talk a little bit about how you think physicists may be modifying the way in which they're you know, conducting their training and their research, and what they maybe have to prepare or be preparing themselves for? You know, looking at that sort of job evolution.
Yeah.
And
You mean, to clarify, do you mean in industry or in academia?
I think both within academia and without. I think it's always, you know, physics, you know, PhDs have a lot to contribute to both sides. Yeah.
I have a very concrete piece of career advice there, which is make short-term plans, not long-term plans. And I want to elaborate just a little bit on that, because if you start talking about what'll things be like in 10 years? Well, on one hand, you have some people many, you know, serious people that say, oh, nothing much is going to change because we're very far away from smarter than human AI. Then you have other people who are saying, well, we're going to have all these amazing tools that are much smarter than us, but it's all going to be fine, and humans are still going to be in high demand on the job market. And then you have people who say, actually, we're all going to be extinct by then. You have people like Jeff Hinton, who in his Nobel Prize acceptance speech was talking about how or he thinks most likely we'll just lose control over this stuff and maybe not go extinct, but still have no influence over what happens. So people are all over the place. And I think you should take very seriously all of these scenarios. None of them can be easily dismissed. What does that mean for practical career choices? It means do not spend a lot of time making plans that rely on one of those outcomes. It's a huge waste of your time. Instead, ask, what is it that's useful to do right now, regardless of which direction this goes? And first of all, being in this course, a great first start, so you can be oriented about what's the state of play and keep following along, and then be very nimble. You know, the day when Kyle and Jim and I and Rick were kids, most people told us, oh, you know, study something and then go work on it for 40 years. Those days are gone. They're never coming back. Instead, what you really want to do is, yeah, be nimble, get a bunch of useful skills, go with them, and then but prepare to keep updating your plan pretty regularly. So I think this school is like the perfect place to do that. If you catch yourself thinking too much about, again, what you're going to do in 10 years, you're wasting your time. You should think about, what do you want to learn now? What do you want to do this year? And one of the biggest things you're going to do this year is that as it moves along, revise your plan for what you're going to do after that, and just, you know, go with the flow.
Yep. Good advice.
Yeah,
Please.
I guess one thing I'd say is that, you know, there are, in the short term, there are more jobs coming up that are kind of like where AI and things like this are appreciated in a kind of physics department, and vice versa. There are more opportunities within academia to do these kinds of hybrid things. You still need to be very, for better or worse, you still need to be very careful, because like a lot of academic norms are still quite conservative. And so, I think if you want to go into industry and do something like that, I think you can bring those tools, and you have a lot of flexibility. In academia, I think it's still important that you somehow execute on some kind of disciplinary excellence or something, and then the AI part is largely like either part of that or is like a bonus or something like that. As much as I wish that there was more flexibility, I think it's just honestly, that's where kind of academia sits. The other part is that there's unfortunately, I'd say kind of a impedance mismatch between, like, you know, in theory, you can move a little bit more nimbly and fast, but in terms of the bigger experiments and what those kind of, you know, physics cultures look like, things are move pretty slow. And one of the things that's a little bit difficult is like, what's going to happen on a kind of 5 to 10 year time scale in terms of like how, like, there's going to be a lot of tension as AI continues to move really quickly. And some fields, like you see in kind of chemistry and protein design and stuff, are like changing very quickly. It's hard to move 3,000 member collaborations and how they do what they do. And so it's on one side you hope you're going to take advantage of it, but it's also like figuring out how to navigate both being quick and nimble and then also working in the context of a kind of slowly moving, somewhat conservative field is going to be a little bit challenging. So I think it depends a little bit on if you want to do academic or not. But I completely agree with Max's point that yeah, the style is changing, and that focus on being nimble, and also there are a lot of the really fundamental things are not changing. I mean, as I think all of us have hinted at, and Max brought up various things about information theory and et cetera. And those are old ideas, and I completely agree that they're still like at the core of a lot of the fundamental things. And we talked about anomaly detection, the fundamental questions and what's fundamentally hard or not about that question, not new. The capabilities are kind of new, and the kinds of tech tools are different. But yeah, so somehow don't give up that kind of deeper long-term thinking, and spend a little bit of time understanding how did people ask these questions before, how did they frame them before. Maybe you end up finding yourself reading a cybernetics book or something, but the people have been thinking about this stuff for a while. So
yeah, sorry, go ahead. Yeah, I just wanted to add a little bit more onto something that Kyle was saying. So it is true that there is this sort of need to be attached to some sort of more traditional field, because in certain academic departments, you will see people sort of take a conservative approach and sort of ask, does this belong in a physics department, et cetera. But something that I think we have seen the last 5 or 10 years, maybe kind of, I'm told that questions, 20 or 30 years ago would have been raised similarly about biophysics. Does biophysics belong in a physics department? Is this physics, et cetera? And now it's a foregone conclusion at most US institutions, at least, that biophysics belongs in a physics department. The boundary is moving, and I think more and more people are considering this to be not only something that you should hire in physics departments for, but also it's opening up new directions, that jobs that previously did not exist, whether it be sort of in computer science or in some sort of new data science direction. And there's more jobs than I certainly now and the last year or two compared to 5 or 6 years ago. So I do think it is positive progress, even if it is still important to do something concrete and disciplinary, which I think was the word that Kyle used. So, on the other hand, I'm someone that came into string theory, 10 or 15 years after the so-called second superstring revolution, which was this historic time in the history of the field where things were really being developed, and it changed so much of what we know about quantum gravity. But I think it's just important to say, what's happening in machine learning and AI, especially with respect to ML for science, I think it's pretty historic. And it's a great time to be getting involved in this direction. And it's natural to be concerned about job prospects. But it is true that I think things are moving the right direction, both with respect to the science. There are better and better and better results, but also with respect to the jobs. And, I'm happy to, share things I've heard privately, examples if people need some encouragement. But, it is true that things are moving a new direction, I think.
I need to drop at the top of the hour now, but just to add the final optimistic thought, I completely agree with Jim. The boundaries are shifting, just like they did for biophysics. And the Nobel Committee this year decided that Jeff Hinton's work is now physics, since that's they gave him the physics Nobel Prize, right? So I think it's quite clear that physics departments, by the time you graduate from whatever your degree you're studying for right now, it's going to be even more obvious that this is something you can do in the physics department, meaning that it's not just the traditional AI for physics that you can do in the physics department, but also a lot of the physics for AI stuff. So, yeah.
Thank you so much. And yes, we are at the top of the hour there. We've got 25 minutes now to take a break. And then my colleague, Sean Newby, will be giving us an opening introductory module that will help make sure that you're well plugged in as far as the rest of the school is concerned. I really want to thank my colleagues so much for their contribution, Jim, Kyle, and Max. It's been fascinating for, obviously, as they all pointed out, they started their careers with different focus that they've moved or accommodated research in an area which probably wasn't on their the list of academic areas they expected to be. involved in when they first started. And obviously, as we heard from the speakers, this was that willingness to be flexible. But I would reiterate, as our speakers did, I think the need, for a sort of rigor that we are very much trained for within physics, and using our natural desire to, explore and explain, systems that we have something to contribute to, machine learning in particular, given our skills set. I don't think many of us want to get in a situation where these systems become simple black boxes, and we certainly understand that we can't trust. I think everybody's already seen just the willingness of these systems to to invent phantom material at a rate that is truly mind-bending. So let's, we're all going to move forward on that basis, but plenty of reason for optimism, plenty of opportunities. So we're going to shut down this part of the of our presentation, and as I say, in 25 minutes now, at 2:30 or 14:30 hours Eastern local, will be starting up again with the introductory module for the workshop. And thank you so much to so many of you for participating today, and thank you for your terrific questions. I hope some of the discussion we've managed to steer it onto it, but thank you again.